nejaké detaily. Dnes budeme nejaké náhľady na to, že čo je to zaujímavé, také súvislosti medzi oblastiami matematiky, ktoré by jedného mohli napadnúť. V teórii čísel, to znamená, poviem to ako number theory, we have different number fields. We have the real numbers. Then we have some group of axioms over here that define this number field. If we erase one, then we arrive at complex numbers. Then again, if we erase one, we arrive at quaternions. And then again, raising another one, we arrive at octonions. Now, if we would raise the last ones that are here, we would lose even the associative property of it, and it would give us nonsense as 2 equals 1, for example, which is pretty much nonsense. And so we know that complex fields, complex numbers introduce imaginary unit, which square is defined to be -1. Over here, we not only have 1, but we have ijk, so something like 3 distant imaginary new axes that are introduced. And the axioms say that ijk product of these two equals -1, and then ij equals k, and so on, which is not important, but just to make this more complete. Then we have a graph theory. Which deals with different graphs and shapes that one can have, which are still reasonable. In 1854, Bernard Euler asked the question, what is the biggest finite shape that is semi-regular? Semi-regular meaning that if we have a shape in which we have a facet, and that's a facet of another part of that shape, then there's some reasonable restrictions on the facet. So it's just a facet with the other one, not a facet of some third or fourth one as well. So that's basically what semi-regular means. And the biggest shape that he had found back in the days was called 4-to-1 polytope, which is a shape that has 240 vertices. It would be very hard for me to draw it right here, but it's an 8-dimensional. It would be an 8-dimensional drawing, and so that's graph theory. This is number theory. Remember that in number theory, it usually deals with discrete mathematics, but I mean things like zeta function and other issues are involved in this field as well. Then we have differential geometry, which is a field of mathematics that deals with spaces and how to describe these spaces. And over there we can think of a regular Euclidean 3-dimensional space, so E3, or in other words R3. So we take 3 real number axes, x, y, z. Can denote them like this, and we have a usual geometry, usual in the sense that we live in that sort of geometry, plus there's a time dimension that is sort of weird because it just flows sort of in one way, but as special relativity suggests, we should treat these 4 as one geometry, and that's geometry of our of the universe we can sense with our senses. All right, so in differential geometry, all the reasonable spaces we can think of, we can divide into categories. One would be a category called real projective spaces, n-dimensional spaces. So, for example, how to construct a real projective space of dimension 2. If you imagine a plane parameterized by x and y, so R2, we can treat this space, or we can re-parameterize it in a way that each point of the space would be parameterized by the distance from the origin, let's call it r, and an angle, let's call it theta. And so each space can be parameterized by these two coordinates. Now, if we construct this two-dimensional space in the following way, that we have our origin, and through that origin we would just have lines, all the possible lines that pass through the origin and are infinitely long. Sound like this. Then we can recast this concept of space by all the lines that go through the origin, you know, at every single angle. Now, if we do this thing, that the point in the infinity, let's say that, you know, I can't draw it, but point at infinity here, we would identify with a point at infinity over here, or at minus infinity, let's say. So we identify these points in all of these lines, we get a real projective space of dimension 2. So we would somehow close that space, you know, we would close it in a manner of identifying the endpoints, and we'd get real projective space. So this was just to illustrate the very concept of projective spaces. But we're going to go further than that. We're going to go further. So, apart from these, we have complex projective spaces. Then we have quaternionic projective spaces. And, of course, we have octonion projective spaces. So, this is what we have in differential geometry. Now, there's another field of mathematics which I find the most appealing, which is group theory. Now in group theory, we deal with symmetries. We deal with the very concept of something being invariant or something being the same. So, as an example, take two-dimensional plane, like a table, for example, and we may place a glass on it. Glass that is symmetrical, so it looks like a cylinder, sort of. And now, how about we observe the cylinder, then turn around, and somebody rotates it a little bit. So suppose somebody rotated it by P4, so by 45 degrees. Now, if we would observe it again, it would look the same to us. So we say that this glass is invariant under rotations which have the axis perpendicular to this plane. So if he would rotate it by 90 degrees or 180 degrees, it would look the same to us. So it's invariant under these rotations. So these rotations can mathematically be described with matrices. If we're in 2D, so we only have x and y here, the matrices would look like this. So it would be cosine the angle of rotation, sine the angle, minus sine the angle, and cosine the angle. So if we would rotate this by 90 degrees, which is pi over 2, it would be just cosine pi over 2, sine pi over 2, minus sine pi over 2, and cosine pi over 2. And all the matrices of this form that realize the rotation of the glass in this plane, yx plane, all the matrices of this form, denote them by A, they are elements of the group of the symmetry of this glass. So there is a group which is SO2. So it's special orthogonal group of dimension 2. Orthogonal means that the matrices, if I take a matrix and multiply it by the transpose of that matrix, it gives me 1, or the identity, which is a 2 by 2 matrix of the form 1, 0, 0, 1. This is the identity in 2 dimensions. So there's a very rigorous definition of a group in mathematics, and the definition says that first axiom of the group is that there exists an identity element. So there exists a transformation or a matrix that, when applied on this, gives me the same thing. That would just be the identity. Then, second axiom of group is that there exists an inverse. So a to the power of minus 1, I'll denote it. So it means if I rotate this by 30 degrees that way, there exists a matrix that rotates it in minus 30 degrees. So that when I apply the rotation, and afterwards I apply the inverse, it just gives me the identity. So it's like nothing was done. And then there's another axiom of group that says that if I apply 2 of different transformations within the group, I'll get a third one which still be in the group. So if I rotate it by 10 degrees and then I rotate it by 20 degrees, so I do 10-degree rotation and a 20-degree rotation, I end up with a different group element, which is a rotation by 30 degrees, but this has to be in the group. So it has to be a matrix that rotates the object in the way that we want. So so this says that the action of the group is closed within the group. So that's just a small caveat of the notion of group and the notion of group theory. Now, if you look at all the so that was SO2. SO2. I haven't fully described the meaning of S and O. So O means orthogonal. So that means matrix times the matrix transpose give us identity. And the special means that it doesn't change the length of anything within the transformation. So in the matrix language, this translates into the fact that the determinant of the matrix A is 1. And that means if we had a vector in this plane, so this is xy plane, this board, and we apply this matrix to the vector, it rotates it, or maybe it just leaves it as it is, but it doesn't change the length of it. So the length stays the same. And this is very, very crucial because SO2 is therefore something that we call an isometry on this space. Isometry. So, isometry. Iso being the same and metry being the length. So it doesn't change the length. If you only had an orthogonal group without the special property, then it might rotate this vector by, let's say, 30 degrees, but it could be twice the length or something like that. So these special orthogonal groups are of big importance in physics as well as in mathematics. Now, all the reasonable symmetries that we can think of in physics usually are either SO, or maybe we have a complex group, so they're SU, so special unitary group, for example, of dimension 2, let's say. So there would be all the matrices, 2 by 2 matrices, that have complex entries, so Z1, Z2, Z3, Z4. So all of these four components are complex. And since it's special, it means that these as well on the complex field, they don't change the length. So again, the determinant of this matrix would be 1. And in this sense, unitary, something different than orthogonal, but it's just a complete analog of what orthogonal was on above the real number field. So in this case, we have a matrix from this group times matrix, but not transposed, but conjugated, complex conjugated, or Hermitian conjugated, and this would give us unity. So that's just another analog of being orthogonal on complex spaces. So all right, now my point about the field of mathematics that deals with group theory is that all the possible algebra, so we have a group, and we can say that 2 by 2 some matrices form a group. Now there's a structure underneath groups that is more fundamental and deeper in a sense. That structure is called an algebra. So we have a group, and underneath it we have something that's called the algebra. And it's just a more fundamental structure because knowing this algebra, we can easily construct all the groups that are above this algebra. But knowing the group, we can only construct the algebra space, let's say, very close to a special point, and this point is unity. So this is the famous thing about spin and SU2 and SO3 algebras. So we say that SU2, SU3, SO3 is a double cover. So it's not SU2, but quotient over Z2. So SO3 is a double cover of SU2, let's say. Okay. And so the algebra is what we're interested in. So now, if we look at all the reasonable algebras that we encounter in physics, we find out, or we learn, that there's only a handful of them. So then there's an AN series, which can be depicted like this, due to Dynkin classification. So it would just be depicted as knots and dashes between the knots. And the number n is the number of the nodes over here. Now there's B series, which looks very, very similar, but there is a double dash between the last two nodes and an arrow pointing towards the last node. Then there's CN series, which is the same, but now the arrow is pointing this way. So the arrow somehow represents fugacity or multiplicity or dominance of the node it's pointed to. So over here, all the nodes are sort of the same, but this is somehow special because there's double dash and there's arrow pointing at it. Now in CN series, the arrow is pointing this way, so somehow all of these are somehow special with respect to this one. Then there's DN series, which at the end has a sort of a fork. So this node has two dashes pointed to two different distinct nodes. So this is very important. And this right here, these four series, that's it. These are all the classical algebras. All the classical algebras. So to be more concrete, AN series is usually related to SU algebras. Alright, I'm just going to write SU. Now BN series is related to SO and now an odd number. So 2n plus 1, I'll denote it. SO groups or algebras. CN series is related to the symplectic form or symplectic groups, so SP 2n. They always have an even dimension. Now DN series is again SO, but this time even dimensional, so I'll denote it by 2n. Now, these are all the classical algebras. There's something more. There's some more algebras which are not general in the sense that they're not defined for any dimension, but they're defined for a certain dimension. So the exceptional cases are G2, which looks something like this: a nod, not two but three dashes, another nod, and an arrow. Now there's F4, which is a nod, dash, nod, double dash with an arrow, nod, dash, nod. And then there's E6, E7, and E8. Now, these exceptional algebras look like this. You have a nod, another nod, another nod, and then a nod up in, a nod above this one, and then 1, 2, 3, 4, 5, 6. Now this would be the same, but we have one more nod here. And now this one, again, 1, 2, 3, 4, 5, 6, 7, 8. Now this is everything that we encounter in physics when it comes to different algebras. Now, my point over here is to show how all these fields of mathematics are linked together, and what's more, one wouldn't exist without the other, and they have a very strong connection. Now I think that each of these fields can be studied, and one can ask deeper and deeper questions, and one can go deeper and deeper in all of these fields. Now I think, now let me give you an example of how these are linked. So it's obvious that from considering a real number field, In differential geometry, one can consider real projective spaces of dimension n. Now, if one asks, what are all the isometries of real projective spaces? So what are all the transformations that preserve length on spaces of this kind? One finds that it's the B and D series. So it's pretty obvious, you know, so it's SO odd and SO even. So it's all of the possible S special orthogonal groups, which is very intuitive. So imagine we have, I don't know, 4-dimensional space, so X, Y, Z, W. One asks, what is the transformation that a vector that would take a vector in this space, rotate it maybe, but preserve its length? So it's going to be SO4, obviously. This is pretty similar to Einstein's special relativity, which takes time as the 0th dimension, and then X, Y, Z as the 3 spatial dimensions. And the only thing that the only thing in which time is special is that the signature of time in the metric tensor, which is something that all physicists know, and it characterizes the dimensions and the form of one differential element of that. Like if we're in time space and we move, you know, what's the difference? What's the differential denoted by ds in which we move? So all these space dimensions have signature 1. So it would be, ds squared, let's say, would be dx squared plus dy squared plus dz squared. But what about time? Since time is somehow different, right? So very brilliantly, we just take dt squared, but put a minus in front of it. So we have minus dt squared plus dx squared plus blah blah. So this is what a square of elementary, shift in this geometry corresponds to. So the metric of space-time denoted by g mu nu would be just a diagonal matrix with -1 here and then 1 1 1 and then all zeros. Okay, now how are these related? So I already said that all the isometries on real projective space and dimensional space are within the Bn and Dn series, so it's SO. Now if we look at isometries on the complex projective spaces, we find that it's not only B and D series, but also AN series, since we have complex special unitary group there, or algebra there, so of course we need something with a complex structure, endowed with a complex structure at hand. So it's also the AN series. Now if we look at isometries on the quaternionic projective spaces, it's not only AN, BN, and DN, but we need one more. We need CN series, so the symplectic forms, symplectic matrices or symplectic groups, in order to have all the isometries of these spaces. And now this is a very intriguing fact, that if we look at isometries of Octonian projective spaces, okay, and we take A, B, C, and D series, which are isometries there, we're still lacking some more isometries. We're still lacking some more. And what we are lacking is exactly all of the exceptional series. So in order to have all the isometries of the octonic projective spaces, octonions being the last reasonable number field, we have to include these 5 series, or algebras, or the groups that are above these structures. And so this is very, very interesting. And then how does graph theory relate to all of this? Well, let me explain you in short.